In this video, we're going to talk about orthogonal sets of vectors. So recall that two vectors u and v are orthogonal if and only if their dot product is 0. Or sometimes we call this the inner product of u and v is 0. So I want to begin with the definition. We say that a set of vectors v1 up until vp that is in Rn, so all of these vectors are in Rn, this set of vectors is orthogonal if vi dotted with vj equals 0 for any I and j that are not the same. So what this is saying is that the vectors in this set are what are called pairwise orthogonal. And what that means is if we look at any two of them, they are orthogonal to each other. So we can similarly define what it means for a set of vectors to be orthonormal. So if we have a set of vectors, v1 up to vp in Rn, that set of vectors is called orthonormal if, well, we need two things. The vectors need to be pairwise orthogonal, and the vectors have to have a length of 1. They have to be unit length. Okay, so let me break both of these down a little bit more. So pairwise orthogonal, well, we saw what that meant above. That means that vi dotted with vj needs to be equal to 0 if I and j are not the same, if those indices I and j are not the same. So what does it mean for vectors to have unit length? Well, that means their length is 1, so the length, this is my notation for length, the length of vi better be equal to 1. And I can rewrite this in terms of the inner product or in terms of the dot product by saying that vi dotted with itself needs to be equal to 1. Because remember that vi dotted with vi, that's the length of vi squared. And if the length of vi squared is 1, that means the length of vi is 1. Because when I square root this, the length is not allowed to be negative 1. The length is not allowed to be a negative number. Okay, so again, vectors are orthonormal if they're pairwise orthogonal, so they need to be orthogonal, and they all have length 1. All right, so now let me state a theorem about orthogonal vectors. Okay, so if we have a set of orthogonal vectors, u1 up until up, then that set is linearly independent. So let's prove this. So the way I'm going to prove that these vectors are linearly independent is I'm going to begin by taking a linear combination of them that equals 0. So let's let 0 equal some linear combination of these vectors. So c1 u1 plus dot 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 plus cp up. Okay. So what I want to do is I need to show that all of these weights, c1 up until cp, are all 0. So one of the reasons why having orthogonal vectors is so nice is, well, when you take the dot product of orthogonal vectors, it's going to be 0. So what I'm going to do with this is I'm actually going to dot both sides of this equation by something. So I'm going to dot both sides by the vector u sub I. Okay, so on the left-hand side, I'll just get 0 dotted with the vector u sub I. On the right-hand side, when I dot it with u sub I, that u sub I is going to sort of distribute to all of these terms. So I'll get c1 u1 dotted with u sub I. And I keep going like that for all the terms. So plus dot dot dot. Somewhere in the middle, we're going to have the term ci ui. That is going to get dotted with u sub I. And then I keep going until I reach the end, which is plus dot 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 plus this last term was cp up, and that's also going to get dotted with u sub I. So the reason why we're allowed to distribute this, dotted with u sub I on the right-hand side is that was one of the properties of the inner product that we talked about last time in section 5.1. Sorry, 6.1. Okay, so now a bunch of the terms here will simplify. When you dot the 0 vector with anything, you get the 0 vector. So this is going to be 0. So we have 0 on the left-hand side. And on the right-hand side, we know that this set u1 up until up is orthogonal. So whenever you dot two of these u's, and these indices are different, like this 1 is different than I, then that dot product is 0. So this dot product is 0. In fact, a bunch of these are 0. The last one is 0. There's only one dot product on the right-hand side that's not 0. And that's this one right here. This one right here is not 0 because this is ui dotted with itself. We're not dotting two different vectors in this set. That's why this is not going to be 0. Okay, so the only thing that survives on the right-hand side is we have the ci term, and then ui dotted with itself. And I'm realizing now there's one key word I forgot to write in the statement of this theorem. So let me add that in. I wanted to also say that this is a set of non-zero vectors. Right, because if the 0 vector is one of the vectors in my set, the vectors are definitely linearly dependent. So I need my vectors to be non-zero vectors. And why that's important is because that means that when we have this ui dotted with itself, so let's just write it down for the time being. So ui dotted with itself. The only way for a vector dotted with itself to be 0 is if the vector itself was 0. So we know that this vector is not 0, because that's an assumption of this theorem that I've added in now. I forgot to do that before. So this term, ui dotted with itself, is not 0. So for the right-hand side to be equal to 0, the only way for this to happen is if ci equals 0. So we've shown that ci equals 0. So similarly, if we had started off by dotting with a different u term, like dotting with u1 or dotting with u2, we could show that all the other ci's are 0. So similarly, all of the ci's, all of these weights, equal 0. And as a result, S is linearly independent. So this theorem is really important. Whenever we have a set of orthogonal non-zero vectors, that set is linearly independent. Okay, so let's state another theorem that's kind of similar to this. Okay, so this next theorem says, if we have vectors u1 up until up, that form an orthogonal basis for w, and w is a subspace of Rn. Okay, and if y is a vector in w, well, that means that we should be able to write it as a linear combination of u1 up until up. So I've written that as y equals c1 u1 plus dot 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 plus cp up. It turns out there's a really quick way to figure out what the weights of this linear combination are whenever these vectors u1 up to up are orthogonal. And that's given by this formula. So ci is y, let me add the vector to this, I forgot to do that. Y, the vector y, dotted with ui, and then divided by ui dotted with ui. Sorry, let's just say ui. So this is true for every single I. For every single index here that's between 1 and p, inclusive. Okay, so how do we prove this? Well, the proof is actually really similar to the theorem that we just proved. So I'm going to begin by letting y equal this linear combination that we have, c1 u1 plus dot 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 plus cp up. So I'm going to begin like that. And because this proof is going to be really similar to that previous theorem, I'd like to give you guys the opportunity, I'd like to give you all the opportunity to pause the video and try this for a couple of minutes. So pause the video for about 2 minutes and see if you can continue the proof. So 4, 3, 2, 1, pause the video. Pause the video for about 2 minutes and try this. Try to continue the proof in the same sort of way. Okay, so hopefully you guys have done that. Hopefully you all have paused the video for a few minutes and tried it. Okay, so let's continue. Let's, just like in that last theorem, let's dot both sides by ui. Okay, so I'll dot y by ui, and let's do the same thing on the other side. So when we do that, we'll get c1 u1 dotted with, so this is orange, ui, plus dot dot dot, plus somewhere in the middle we'll have the term ci ui, and now we dot it with ui, and then plus dot dot dot, plus finally we have cp up, and now we dot that with ui, so dot this with ui, and just like we saw before, a bunch of these terms are going to be 0. So in fact, all the terms on the right hand side are going to be 0 except for this term right here. Alright, so what this leaves us with is, well, we have y dotted with ui on the left, and on the right we have ci times ui dotted with ui. Let's put vectors, arrows on those. Alright, so now dividing both sides by this. So this is just a scalar. After you dot these two vectors, this is a scalar, so we can divide by it. We get that ci equals y dotted with ui over ui dotted with itself. And that's what we wanted to show. That's this formula that we were trying to get. Alright, so let's do an example where we apply this theorem, where we see why it's useful to have this formula for these coefficients of this linear combination. Alright, so here is the example. So x is the vector 7, negative 1, and let's try to write this as a linear combination of these two vectors, b1 and b2. Alright, so first, let's check that the two vectors, b1 and b2, are actually orthogonal. So if we take the dot product of these two vectors, or the inner product of them, so b1 dotted with b2. So we'll get 2 times 2 plus negative 1 times 4. That's 4 minus 4, which is 0. So that means that b1, whoops, sorry, the video just kind of jumped there on my screen. So b1 and b2 are orthogonal. So because they're orthogonal, we're going to be able to use the previous theorem to write down what the weights are of this linear combination. Okay, so for the solution, what we're trying to do is write x in the form c1 times the first vector plus c2 times the second vector. So since b1 and b2 are orthogonal, we can use the previous theorem's formula. So c1 is going to be x, my vector, dotted with b1 divided by b1 dotted with itself. Okay, so now if we take this the dot products that we see here, so if we do x dotted with a b1, so we'll get 7 times 2 plus negative 1 times negative 1 times negative 1 on the numerator. On the denominator, we have b1 dotted with itself. So that'll give us first 2 times 2, and then plus negative 1 times negative 1. And simplifying this, on the numerator, we have 15. On the denominator, we have 5. So that gives us 3. So this first coefficient, c1, is going to be 3. So let's do the same thing to figure out c2. So c2 will be equal to x dotted with b2 over b2 dotted with b2. So what's x dotted with b2? So let's see, we'll have 7 times 2 first. So 7 times 2 plus negative 1 times 4. And then for b2 dotted with itself, we will have, so on the denominator, we'll have 2 times 2 plus 4 times 4. So overall, we have 14 minus 4 on the top, which is 10. On the denominator, we have 20. So that gives us 1/2. Okay, so at this point, we actually have both of these weights, both of these coefficients. So what this tells us is, well, the vector 7, 1 equals, what does it equal? It equals 3 times b1, and b1 was 2, negative 1, plus the next coefficient is 1/2. 1/2 times the next vector, b2, which was 2, 4. So one of the reasons why this is nice, so let me write this on the side. This is nice. This is nice because with orthogonal vectors, we can find the weights of our linear combination without an augmented matrix. Right, because normally to do this, if we want to write a vector as a linear combination of other vectors and figure out, well, what are the coefficients, what are these weights that do that, we'd have to form an augmented matrix. So when these vectors, b1 and b2, or if there are more of them, when they are orthogonal, this previous theorem and its formula lets us find these weights without having to form the augmented matrix. And that's why it's nice. So drawing a picture of what's going on here. All right, so let's draw a picture. All right, so let me draw some axes. So the vector b1 was 2, -1. So b1 looks something like this. So b1. b2 is the vector 2, 4. So 2, 4 looks something like that. And these two are supposed to be orthogonal. We check that they're orthogonal. So b1 and b2 are orthogonal. The vector x was this vector. Oops, sorry, I think I miswrote this. I think this should have been 7, -1. Let me just double check that. 7, -1, was it 7, -1? Sorry, I scrolled too far up. Yeah, it was 7, -1. I just miswrote that. Okay, so 7, -1 there. So we draw 7, -1. 7, -1 will look something like this. So that's our vector x. So what is happening here is if we extend this vector that b1 is on, is the direction that's going in with this dashed line. And then if I draw perpendiculars from where x is to this line that b1 is on, and to this line that b2 is on, the length of this segment here is 3b1. And notice that's the coefficient that we saw here. So this is the vector b1, this is the vector b2. And the length of this segment over here, this is 1/2 b2. So that's what we're sort of doing here. We're taking our vector x and we're sort of decomposing it into these components in these orthogonal directions. Let's just remind ourselves. So this coefficient 3, the way we determined that was we saw that 3 was x dotted with b1 divided by b1 dotted with b1. That was the formula that we used to determine that coefficient. Okay, so this formula leads us to our next definition. So this is the notion of an orthogonal projection. So we say that the orthogonal projection of a vector y, which is in Rn, onto a vector u, which is in Rn, is given by the following formula. So it says that the projection of y, the way I read this is I say the projection of y onto u equals the following formula. So let's break this down a little bit. Okay, so first off, when it says that we're projecting onto a vector, what that technically means is we're projecting onto the span of that vector. And visually, the span of this vector is going to be a line. So we're going to be assuming that u is non-zero here. Okay, and then breaking down this formula a little bit more. So this fraction is this fraction that we saw here. And this fraction is going to represent a scalar. Because after we take dot products, we get scalars. And this u that we have here is a vector. So we have a scalar being multiplied by the vector u. As a result, this entire thing should be in the span of u, because it's a multiple of u. Alright, so let's draw a picture of this. Alright, so drawing a picture of this, so let's draw some axes. And let me draw a vector u. Let's draw a vector u, and then we'll draw a vector y. So y. So when we project y onto u, we're projecting the tip of y sort of perpendicularly onto u. So draw a perpendicular. So I have a perpendicular. And the projection is this vector. This blue vector is the projection of y onto u, onto the span of u. In other words, onto the line that u is in.